All right, missing data, lecture 4G. Let's dive in. One thing that I've conveniently not exposed you to in any example in this class is a data frame that had NA values that was sent to Stan. Have anybody tried to do that? Has anybody tried to send Stan some NA data? Doesn't go well, does it? It's not going to go well. All right, let's talk about it. We're going to use our conspiracy theory data. And if you try to send Stan observed data in a model that has an NA value, Stan just quits. It's like, nah, nope, you can't be doing that, right? This is default because Stan doesn't model missing data. So here's an interesting thing for you. If you grab JAGS, just another Gibbs sampler, and you send it missing data, JAGS is totally fine with it. Totally good. And the reason for it is JAGS will take your model and it will use Gibbs sampling to impute your data based on your model. So it will continue on, but it will impute data that's missing. Stan, not so much. Speaking of missing data, by the way, if anybody's interested in the whole philosophy of missing data or topic of missing data, I'm teaching a class next semester on missing data. You're welcome to join me. It's going to be great. We're going to talk about how to do data when you don't have any. We're going to make stuff up all year long. But that being said, I will say I'm going to try to treat it missing data from a multiple perspectives. Some more in the social science perspective using Craig Ender's second edition of his book. But then we're going to get into missing data in psychometrics. There's impacts of missing data on computerized adaptive assessments. There's impacts of missing data on secondary analyses if you treat your latent variables as known when they come out. So both of those are going to show up as well. So there's my pitch. Please join us if you like. It'll be in person. It'll be great. We'll have party every Wednesday. Every Wednesday afternoon, it'll be just a party of missing data. Or better yet, maybe the party will be the missing data. One of the two. Anyway, one of those is going to be it. My humor is not yet back yet. I guess I'm gonna have to keep waiting. All right. So what do we do? Stan won't handle missing data. We just switch to JAGS and call it good? No. Instead, we're going to make Stan work with the data that we do have. That's the trick. That doesn't mean that we remove cases. It means that we let Stan know which variables are NA and which values of an observation are NA and which are not. Okay? Okay. So we're going to start here by taking our example data set, and I'm just going to set the very first value. Son of a Templin. Come on, disgust yourself here. We're going to take the very first items for the first person and change their response from whatever it was to missing, just to see what happens. Okay? Okay. We're going to use the syntax for the multidimensional model in the last lecture, our multidimensional model, but instead I'm just going to trick it a little bit and use a Q matrix with one column. So even though I'm using the multidimensional model syntax, I have a unidimensional model I'm running because it all runs on the Q matrix, right? Cool? I like that. And a word to you, if you're going to use Bayes for any psychometric stuff, grab that Q matrix version as a starting point, the one that has multi dimensions, because it generalizes. It'll run multiple dimensions for you. Okay, so for the model block, what we have to do is now what we have to tell Stan for Y. Remember, previously we had each item listed here. But now we have to give Stan the set of data that are observed for that item. So I'm going to be creating a brand new input data set where the input data set only provides Stan a list of rows in my data where I have actual numbers, not missing data. Okay? That's the hard part. So instead, so for each item, so remember this first item, I don't have 177 responses. I have 176, right? So what observed will tell me for this item will say, I have, which are the rows of my original data that have data? And that's row 2 down to row 177. So what you will have in this observed matrix is which values in my original data were there. And so what that means is I can go and modify this to build a likelihood that just skips over the data that are missing. And it turns out when you build a maximum like any type of likelihood function, if you have missing data and you omit the missing data from the likelihood, but you still calculate the likelihood on what's remaining, that sounds like cheating, but it turns out to be what we do in most ML or likelihood-based methods, including Bayes. And it turns out that actually has fairly okay properties about missing data. I haven't, next year you'll learn about certain characteristics of missing data. What this assumes is that data are missing at random, which is a fairly common assumption. So turns out all we have to do is make Stan run on what we have, and that just involves us building this observed matrix. So how do we build it? Let's talk about it for a little bit here. Here's our data block. Most of this is the same as you've seen before, but instead, first I'm building in a three-dimensional array of what's observed by items and observations itself, and I'm telling it how many are observed itself. So let me grab my code here. I want to walk through this just a bit. Give me just a second to get this moving. Okay. That's where it says Y has NA values. Here's my missing data syntax. Let's build observed real quick. So the observed matrix is the following. What I want to tell it is I have this vector called n observed. And for each each variable where I have data, it tells me the count of observations that are not missing. Right? That's our first bit of input. We find it by basically saying how many variables are not missing, or how many observations are not missing for each column of our data set. This other matrix observed right here, it, for each variable that I'm going to input, so V1 corresponds to item 1, this gives us which row of the data is not missing. And you'll note the very first row of this starts with the number 2. And that's because it's corresponding to item 1, right? Our conspiracy theory data. And I had made an NA. Where did that go? Conspiracy items. That's it. This very first value is NA in my data. So really, I have data in row 2 all the way down to row 177. And I need to tell Stan that. So my observed matrix, the very first column of it, refers to that first variable. And it tells Stan, only look at the rows that are listed in this column, in this case, from 2 down to 177. You'll note the 177th value right here, the very last row, is a -1, but that's okay because in my Stan code, I'm actually going to not use that -1 value. It's actually going to show up right here, that 1 through n observed. It says, look only in rows 1 down through however many I've observed, in this case 176, and use only those values. So that is what we're doing. We'll use. Okay. So this observed matrix right here is our first bit. We need basically to tell Stan which data to use. We also need to then transform our data. So if conspiracy items, this data frame has an NA in it, I need, even if I don't model this NA in Stan, even if I set my code up to skip the NA, Stan will know where there's an NA there. It checks it and it will throw an error. So next I need to go and change my data to remove the NA altogether, and in its place put a value that I can read if I'm reading it as a human is allowed but negative, like not part of the range of data. Right? This may be like, if any of you, I don't know about you, but when I started in statistics, did you ever get a data frame? What was your missing data code in your early statistics classes? I believe 99 for whatever reason. Anybody have 99 for missing data? Sounds good, right? 99. And then as an instructor, the first thing I would always check when I give out homework, like on people's real data, like take a look at your item means. Why? Because if you have a 99 and your other values are between 1 and 5, that means you're going to be like 50, right? Remember that? So we've got that going on here. And if we're not careful, we might model a 99 or something along those lines. But what I'm going to do is switch and basically say every variable that's missing, I'm just going to call -1. And if I coded it correctly, Stan will not use that value. Okay? So now I'm going to fill in -1 for my data. And now conspiracy items, if I open that up again, you'll see it has a -1. No. Hmm. What? Oh, Y. That's why. I'm building stand data and it's in the value of Y right here. So that Y has a -1 in that spot. Okay? Okay. So then that is what we end up having. We're importing this observed and n observed, the vector of n observed, array of n observed for every item. This is just telling us the number of observed values in each item. This observed matrix tells us which values those were. And then we can build stand to go and estimate data. And when we do that, we make a nonsense value. We run Stan. Stan runs. Ta-da! Hooray! Not a problem. I will also note, though, and I'll leave it to you to think about. Uh, so this is a quick lecture, super quick, but somewhat incomplete. Here's our likelihoods. Basically, here's what's happening. Basically, if when we build a posterior likelihood based on our data, we usually take the product across all people. But if a person's missing an item, what we end up doing is just substituting that likelihood value with a 1. We just calculate it across the items that happen to be there. Um, there are some ramifications for this. I've just mentioned this before. Um, we're just This is a stronger method for analysis. We're not doing case-wise deletion. We're not dropping an entire observation just because they miss one data point. We just calculated things a little bit differently for them. Other ramifications that you would find would be, for instance, person one's, like where the missing data happen to be. Like person one, when we calculate that person's data, we're actually calculating it on 9 items, not 10. So you would expect it to be a different value than it would have been if we had the full data set for it, right? So not only will we have a different posterior standard mean and posterior standard deviation, but the more missing data we have for a person, the bigger their posterior standard deviation for theta will be. You would expect that, right? Because it's just, we have less information. The other thing I'll note is I'm going to ask you a question. I'm going to combine the last 2 lectures. But here, I don't calculate model fit. But if I wanted to, how would I do it? Turns out I would use the same type of process, right? So for PPMC, um, I may omit the first case to go and fill in data, right? Or I may just fill it in anyway, like as if I had observed it. Either way. For LOO, right, the expected log posterior density, turns out this ordered logistic underscore LPMF that we used in our last lecture works the same. So I would just basically give it the same call and calculate the same statistics, even if the data are missing as well too. I just didn't do this in this example. So missing data, quick topic. All done. There you have it. Question, Vladimir. Mhm. We can do either, right? Because if we generate data for the cases that we didn't observe, we just have more simulated data. It's going to look like our model. Um, those cases we didn't observe, though, aren't going to matter on our observed, the red dashed line that I had, right? So if we think of PPMC, there's the predictive distribution that we had, and then there was the red dashed line, was the observed value. In the predictive distribution, whether we simulate data for that person or not, it's not going to change much, right? I guess we may get a little bit smaller interval, so maybe we would want to skip it for people. But for the observed distribution, that because we're missing their data aren't going to contribute to that statistic. So it's not going to affect the observed distribution. We probably should take care for the predictive distribution, but that's another topic for another time. Good question, though. All right. Any other questions? All right. We are out of time for today. So at that note, I will thank all of you for being here. I will say have a great fall break. We have no class next week. When we return from fall break, I'll have the last two lectures on that Tuesday, and then the rest of the week will be for project work or other questions that you may have. Or if you have a type of model and you want me to try to code it on the fly, I'll do it. Bring it. Okay? Okay. And then the week after that will be project presentations, and I will send out a sign up sheet next in the next few, in the beginning of the week after fall break for when to sign up for presenting. If you have questions about anything, I'll still be on email. Shoot me emails. I will not have office hours next week, though. So, a heads up. All right. All right, everybody. Have a great rest of your week. Good to see you. And see you after the break. Thank you.